My is just on the preprint, which I just wrote maybe 2 weeks ago, and I put in archive. It is work number 4. Nonlinear homomorphisms of algebra functions are induced by sigmorphisms. It's very interesting case where the title of my preprint is the main statement.
Я сразу слышу звук. Объяснит. Сейчас, во-первых.
Okay. So my talk will be founded on this work. Now I will speak about.
Ты переименуйся опять. Кстати, тогда не переименовался обратно.
Не важно это.
Не, ну это не очень.
Сейчас.
Русик, звук.
May I speak? Yes. I will
Yes,
speak
please
about
continue.
formal functionals and nonlinear. I will explain you what is it formal functionals and what's nonlinear homomorphisms. I realize that already people are a little bit angry on this definition, but okay, I understand. I will formulate the conjecture, main conjecture. Then after it, I will try to define what is it sigmorphisms. We'll consider examples of sigmorphisms, and we'll give ideas of the proof of theorem. Okay. In 2014, Ted Voroner introduced In fact, it is he introduced it. He had very important and very special case. We had to find for him. With him, I and Ted Voroner, we were working about 2-3 years for finding nonlinear map between algebra functions, which transform one homotopy Poisson algebra to another Poisson algebra. And for purposes, just for solving this problem, Ted Voroner introduced the notion of sigmorphism. So the notion of sigmorphism, what is it? I will try to explain today. And I'm sure that it will be, many people will be desperate because it is not so easy to explain what is it. But the notion of sigmorphism was created by Ted just for solving this problem. 5 years, even more than 6 years passed after this notion came to the life. Honestly, during these 6 years, I and Ted Voroner, I think that Ted will agree with me, that we had many different attempts to explain during seminars what is it sigmorphism. Usually, almost all our attempts were not successful. The conception of sigmorphism is very difficult to digest. It's very difficult to understand what is it about. Okay, I'm sorry for this pessimistic introduction, but it is my opinion that the way how sigmorphisms are defined, it's not so easy to explain us, at least for me and I think for Ted Voroner too. But immediately when Ted Voroner introduced sigmorphisms, we realized that they obey very important property, that in spite of the fact that sigmorphisms are induced pullbacks of the functions, which are nonlinear maps, but differentials of these pullbacks are usual homomorphisms. And the following conjecture was formulated, that an arbitrary nonlinear homomorphism, the word nonlinear homomorphism, I will explain what it means, but nonlinear homomorphism means nonlinear map such that differential is okay, is good. And the following conjecture was formulated, that an arbitrary nonlinear homomorphism of algebra of smooth functions is generated by some sigmorphisms. Of course, about many years we were trying to prove this conjecture. And in some sense, I gave a proof of this conjecture, but I proved this conjecture in the class of formal functionals. I remember very well, I liked very much the remark which Albert Solomonovich Schwarz, whom I met 4 months ago in Luxembourg, he told the following phrase when I was explaining him what is it sigmorphism? He told me, listen, he said me the following, that I don't know, is this conjecture right or is this conjecture wrong? But in all the cases, the right definition of sigmorphism have to be in terms of nonlinear homomorphism, so-called nonlinear homomorphism. Okay, after this introduction, let me continue. So, the beginning is standard. We know that if we have arbitrary map from manifold M, from M to N, arbitrary morphism, this morphism induces pullback of the functions on N goes to the functions on M. It is standard thing. And people usually don't, sometimes people use language of points. They say map from M to N. Sometimes people use language of algebra functions. It is so-called very famous Gelfand-Kolmogorov duality, which 20th century, okay, many things pass. But of course, the map induces pullback, and this pullback is usual homomorphism of functions. And you can speak in terms of the map, or you can speak in terms of in terms of pullback. What is sigmorphism? I will try to define what is sigmorphism, but from very beginning, I would like to tell you that in the interesting cases, sigmorphism defines nonlinear map. So sigmorphism, it is some formal conception from M to N. It defines nonlinear transformations of algebra functions on N to algebra functions on N. Usually, of course, in some degenerate, in some stupid cases, it can be simple linear transformation, but usually it is nonlinear transformation. Now, immediately, Ted Voronov realized that this map which he defined, and which I will speak about a little bit later, obeys to very interesting property, that in spite of the fact that sigmorphism from M to N defines nonlinear maps from functions on M to functions on M, but however, it obeys to following property, following condition. Differential of this map is usual pullback. So if you consider for arbitrary function G, if you consider infinitesimal changing function G on epsilon h, function on epsilon h, where epsilon square equals 0, formal parameter, then the difference of the value of the functionals on the function G plus epsilon h and the value of function on G equals to the epsilon h on some function. He suggested this type of the maps to call nonlinear homomorphism. Of course, it is not, there are many critics of this definition, and today I heard it, but it is definition which Ted Voronov gave. Definition, let AB be two algebras, a map L from an algebra A to algebra is called nonlinear homomorphism if at an arbitrary element of algebra its derivative is homomorphism of the algebra A to algebra B. Okay, and after giving this definition, we are attempting to formulate the following conjecture, that because sigmorphism, I still didn't define what is sigmorphism, but we believe that sigmorphism in some way defines a map from functions on N to functions on N. But okay, if we have sigmorphism, the pullback, it defines pullback. Here, I'm sorry, from functions to N to M. I'm sorry, yeah, I did wrong, but so, theorem. Is it true that every nonlinear homomorphism from algebra Cm to algebra Cn is induced by some sigmorphism? I'm sorry, here it has to be algebra functions on N to algebra functions on M. Here I confuse. I'm terribly sorry. I did my apologies. In this theorem, okay, I will formulate it again. So every sigmorphism defines map, every sigmorphism, let me repeat again, every sigmorphism from M to N defines map on the functions from the functions on N to the functions on M? And is it true, the theorem, is it true that every map from functions on N to functions on M is induced by some sigmorphisms? I gave a proof of this conjecture during, yes. Oh, thank you very much. Thank you very much, yes. Here has to be N and here has to be M. Thank you very much for somebody who did it. I'm sorry, I did a mistake. Okay, I will prove this conjecture, but I will prove this conjecture in the class of formal functionals, because I will define formal functionals in a way that so I will define what is formal functional. Then when I will define what is sigmorphism. Okay, what is it formal functional? Suppose we have algebra functions on N and algebra functions on M. We say that L of G is formal functional from N to M if for every smooth function N, we have series, look here, we have series of the maps at 0x, it is just usual smooth function. L1xg, it is map of order 1. L2xg, it is map of order 2. L3xg, it is map of order 3, and so on. So we consider sequence of maps from and combinations, all sequence of these maps. Of course, I don't speak about convergence. I don't care about all these things. I will call it formal functional. So when I write formal functional, in every term, it is usual functional of order G, and the functional of order R of order N of order R. The functional of order R means that it can be expressed in the following way, where kernel is an arbitrary generalized function. So I repeat again, formal functional for me, it is sequence of functionals. Every sequence functionals of order R, where R takes value 0, 1, 2, 3, n. For example, let me consider an example.
Is X in M here? X is a point in M?
X is a point in M, yes. X is a point in M, yes. Yes, X is a point in M. And Y is a point, okay. Let's consider example. Let's consider for every functions, let's consider example, yes. Consider for every function G on R, we consider sum of zero part, it is just usual smooth function. Then I take the value of the function G on Y equals f of x. And the third term, I take the value of G multiplied on value of its derivative. So here I have zero functional of order 0. It is functional of order 1, which assign to every function G the value of function G on fx. And third functional, we assign to every function G, we assign again function of f of second order. Okay, it is example of formal functional. Formal functional can be considered as a sequence of functionals. Every function LR, it is very well defined genuine functional, and it has order R in G with values in smooth functions on N. But some of these functionals in general maybe have no any meaning. The problem is that sigmorphism, which I am going now to define and which TED defines, they take values, they represent formal functionals. You cannot say that sigmorphism, it is just a map which is assigned to function. It is formal function. So the next thing that I will consider, I will define sigmorphism. I will try to define sigmorphism. But I'm sorry, my definition will be a little bit formal because the main reason of my talk is not sigmorphism, it is some very important properties of them. Okay, suppose we have two manifolds, one manifold M with coordinates x and manifold N with local coordinates y, a. For every function on N, to define sigmorphism from M to N, we have to define a map which assigns to every function on smooth function on M some of the functions on M. For our construction, we will need very much cotangent bundles. So we will use xi pg, it is coordinates of cotangent bundle over M. X, it is point on M, and P, it is momenta, conjugate momenta. And for N, we have YA, QB. Y, it is point on N, and QB, it is conjugate momentum. Okay, so the next construction, which I will use for defining sigmorphism, will make you little, I'm terribly sorry, but maybe after 2, 3 slides, 3, 4 slides, I will explain it. Some action, I will define some object which generates this sigmorphism. So on the next slide, I will show you sigmorphism, but now I will define your object. But from very beginning, this object is something which makes angry any mathematician who look at it, because I cannot define, I don't know how to define it in a good geometrical way. In spite of the fact that it is good geometrical object, it depends on the coordinates x of the manifold M, and it depends on the, Sxq depends on coordinates x of manifold M, and it depends on momenta of N. So it depends on half coordinates of M, T star M, and half coordinates in T star M. And here we have to remember the formalism of generating functions of Landau-Lifshitz, where Arnold says that it is, I'm sorry, I don't know how to say it in English, but there is expression, удручающий неинвариантный. It is very, very awfully non-invariant language. The language which Ted Voronos used for defining sigmorphism, the main object that he used, it is so-called generating function. But now, look, this generating function I will call action. Why I will call action, I will explain a little bit later. Because maybe intuition of people who know what is action in classical mechanics will understand better what object is for. But I repeat again, the object Sxq, which we wrote in local coordinate as a formal function, here it is 0 part, it is part linear on Q, it is part second derivatives on Q, and so on. In fact, it is geometrical object. If you change coordinates, it transforms from one coordinate to another. I don't want to go to these details, but maybe I will speak about meaning of this S. But nevertheless, the sigmorphism, which I will define on the next slide, is defined in terms of this formal function S, which is sum of the functions. S0x is a function on X, it is linear function on Q, it is quadratic function on Q, and so on. So now, to define sigmorphism, we define a map from the algebra of functions on N to algebra of functions on N. This map we define in the following way. And here, to every function g on y, which depends on coordinates on N, we assign the following object. Of course, you will look at this object and say, but what it depends on? It depends on y, it depends on x and q. But here I put YAX, it is usual map. I put conditions that it obeys the following condition. These two conditions makes us to think that right-hand side of this expression, it's like Legendre transformation. Right-hand side of this expression does not depend on x. Because if you, sorry, does not depend on y and q. Because right-hand side, we put the function on y, we take function of y plus function on xq. But because of these conditions, right-hand side does not depend on y and does not depend on q. And we come to function on x. Of course, it is formal function. It is sum of the functions. Here I have worse. I have formal map ya of x. It is a map from x to m, but it is sum of the maps. So all the objects that I'm working with, it is some series in expansion. So mathematically, I don't care about convergence of this series. Of course, I can say nothing about it. I just write formal series. Okay, I will give you an example of sigmorphism, but I repeat again, sigmorphism, it is something which needs another time, another day, another time to speak about, and I don't want to speak today about what's definition of sigmorphism. I will try to give just 2-3 formulas for sigmorphism. You see on the transparent, when I wrote ya, it is ds by dq, we can define expression for formal map. Having function s on xq, we can define this map. Beginning of this map is a usual map, but the next object, next term, it depends on q. So we have recurrent series of the maps, and we come to the map which first term is genuine map, second term depends on the function g, and so on. Let me write, I just will look, I will show you one formula, how looks sigmorphism, and maybe you will excuse me for not explaining how I came to this formula. I just wrote you expression for formal functional FSG up to third order. So if you have generating functions S, by this generating function to every function G correspond formal sum of the functionals. This is zero order functional, this is first order functional, this is second order functional, this is third order functional. I'm sorry, but to write fourth order functional, it's very, very troublesome. It's series of the functionals plus tenth of order for G. You see, so I just wrote typical example of formal functional. This formal functional is the zeroth term, it is just usual function. First term depends on function G. Second term, it is quadratically depends on function G. Third term depends cubically, and so on. Okay. Just before going to the theorem and speaking about, let me show you examples of sigmorphism. Of course, you are listening me. I'm speaking about very strange and complicated formulae which.
Hovik, can I ask a question?
Yes, of course.
The left-hand side, it's supposed to be the value of this pullback function at a point x.
The left-hand side is formal, yes, okay.
The value, let me just clarify my question. So the point is, it's very surprising and strange that you have a term, which is maybe even the dominant term, which is independent of G. So the value of this pullback function at the point x has a term which is independent of G.
Okay, Ian, just 1 second. When I say the formal functional, it is not value, it is formal sum. When I say formal series, yes, it is not value. It is why I always use the word formal functional. For every function g of y, the first term, it is value. Second term, it's value, but the sum of this term, it is not value.
So where does it live then? Where does it live? What?
Okay, it is why I say that it is formal functional.
I don't know what's okay.
Every no, okay.
Sorry.
No. From the very beginning, I told expressions that I consider formal functionals. Every functional lives on sent function from G to function on X. Some of these functionals I consider as a formal functional. I repeat again, some of functional have no physical meaning, have no mathematical meaning. Mathematical meaning has every functional. It is what I call formal functional. Maybe my definition is not good. But what I'm telling about that I consider series of these functionals. Okay, now let's do the following exercise, which is, I think, is very important. Reconstructing an action. We can think, okay, it is something which is forbidden, but maybe you see, you can see, so sigmorphism is defined by the function S. Sx, we can think about as a classical function, and sigmorphism as a quantum object. Okay, it maybe gives you some idea to think about. But for example, when I'm thinking about sigmorphism, I always like to think that sigmorphism is object which is not so good defined, but the classical object, it's action which is better defined. Okay.
Sorry, can I also ask a question, Ovik? Can I ask a question?
Yes.
About the previous slide where you gave this formal functional.
Yes.
So, well, it's too far. I mean, it was just the previous one.
Yes. This?
No. Where you gave this formula for S combined with G's.
Yes. Okay. It's very important.
This one, yes. So you see, when I'm looking at this formula, so I like to think about it as okay, you have a kind of graph with S vertices and G vertices connected to each other, right? So a two-colored graph. And do I understand that this graph must be a tree?
I tried that. No, in the case if it is quadratic, you can think in terms of Feynman diagrams. I was trying to think in terms of graph about this combinatorial. It didn't work. Okay, the answer is you ask very good question. Of course, I really try to think in terms of the graphs, in terms of Feynman diagrams. For the case if action possesses terms of order 0, 1, and 2, it worked. But if action possesses terms of order 3, the number of vertices become much more and more at every term. Okay, I tried to work in terms of Feynman diagrams. It didn't work, but it is really very good. Of course, this is intuition which helped me very much, but I couldn't work in terms of that. But question is okay. You asked very good question, Sergey. Now, I just want to say that of course, you can consider value of the functional on linear function. If you consider linear function, you will reconstruct action. It's very simple formula, just maybe we will need it. But I want to tell you another thing. Let's consider example of sigmorphism. I don't like this example, but always when I have talk, I consider example of sigmorphism, but I will call it very bad, very degenerate, very stupid sigmorphism. Let's consider the case where characteristic function action is just linear in Q. In this case, we will have just usual map. It's very easy exercise. I don't want to go to details. So if we have generating function which possess only linear terms on Q, we come to example of the generate sigmorphism, which is just a usual function. I don't consider this example is good. This example sounds like if student asks, if I explain student what's manifold, student asks me, can you give me an example of manifold? I say, let's consider point, or let's consider line. Of course, line is manifold, but much better to give example of sphere. Okay, my next example, my next slide will be about why I call generating function an action. I cannot give you exact answer, but as physicist, I understand that action from... Sorry? Somebody have question? Sorry. Hello?
I think it was a mistake, Hovik. I think it was a
Where?
technical mistake, probably.
Where mistake here?
I think there was a technical problem. I don't think it was a question.
Okay, that will be
Continue.
Recall what is action. Now I want to argue that the object that I considered, main object which defines sigmorphisms, I call that action generated X machine. And it was remarkable. We will explain why we call function action. Now just let's recall. Let's recall what's action in classical mechanics. If you have Lagrangian or Hamiltonian, okay, in terms of Lagrangian, you can consider function which depends on initial point x, final point y, and time t. You consider trajectory of the particle which begins at the point x, ends at the point y, and it is so-called classical action. We know very well that when we go to that, all physicists learn what is classical action, because classical action helps us to understand what happens in quantum mechanics. When you are engineer and you don't need to learn what is classical action. Okay, you can learn it. But classical action, which you can define in terms of classical mechanics, in fact, we badly need for quantum mechanics. And now for classical action, which is function of x, y, and t, one can define the object which looks like the object which we consider. It is classical action, but Legendre transformation of classical action in terms of y. Now let's consider example. Consider free particle. For free particle, Lagrangian is this, Hamiltonian is this, usual action, and classical, and it is action. Okay, we can consider action, we can consider Legendre transformation in physics. It is not so important what I consider, but Legendre transformation of action, it is something which has very good physical meaning. For harmonic oscillator, it is very beautiful calculations. And you know that in quantum mechanics, particle moves from the point to point in classical mechanics to make action minimum, and in quantum mechanics, it moves all. Okay, conception of action gives us so many ideas. And it is not surprised that we've proved the following theorem, which the next theorem justifies why I call it action. Let's consider standard Hamilton-Jacobi equation for the function f. Just, it is problem from the classical mechanics. Let's consider differential equation with Hamiltonian, with initial condition g. Now, it is very, very beautiful theorem that the solution of this equation, it's nothing that you can take apply pullback of sigma diffeomorphism for function g, and you will come to function f. So this example gives you another example of sigmorphism, but it is sig diffeomorphism because here manifold M is the same. But why I like this example here, we see that action, which is quadratic, plays very important role. And honestly, we did very good, very interesting work where we showed application of sigmorphisms with Ted Voronov in spins and in, okay, it is a work which we did last year, but now it is the main topic. I just want to tell you that here we see that action plays very important role. And of course, action, you can say that sigmorphism that I defined, it was from two different manifolds. But who says me we can consider action as a function of points of the first manifold and second manifold? It's very interesting things which appear here. So conception of action makes it interesting. But okay, let's return to our object. Second thing, I have to explain you why sigmorphisms are so important. Why sigmorphisms are so important. I will try, of course, here I will do the following. Usually when I did on seminars, I spoke about homotopy Poisson brackets. But to speak about homotopy Poisson brackets, we have to speak about supermanifolds. And it is I have no time to speak now much about supermanifold. So I will try to use the word super as little as possible. So we just consider cotangent bundle to M, and we consider formal Hamiltonian on cotangent bundle. And pay attention that if you have arbitrary Hamiltonian, you can define collection of scalar products on the manifold M. Of course, we all understand very well that it is the way to come to homotopy Poisson bracket. But I don't want to use today the word homotopy Poisson bracket because I don't want to use today the word supermanifold. So if we have arbitrary manifold, arbitrary Hamiltonian on cotangent bundle, I can define empty bracket. I can define bracket of function of one function with itself. I can define bracket of two functions. I can define bracket of R functions. So I can define collection of brackets. What it has a meaning? Of course, in the real life, it's real life. It is homotopy Poisson brackets. But to have homotopy Poisson bracket where I have to have homological vector field, I don't want to speak about this notion. I speak just about collection of brackets. Now, it is the theorem. Suppose we have collection of brackets on M, which is induced by Hamiltonian on M, and we have collection of brackets on N. It is this theorem explains why Ted Voronov did sigmorphism. We need very much, we badly need a map from one manifold to another manifold, which sends homotopy Poisson bracket to another homotopy Poisson bracket. In our application, in questions that we studied with Ted, we had many cases where we had very good, very noble scope and bracket on one manifold and another manifold. We had series of causal brackets, and we wanted to make transformation from one manifold to another manifold. And this theorem helps us to do this transformation. Of course, here I formulate one example of this theorem because I cannot formulate this theorem because I need supermanifold, but I don't want now to use supermanifold. Okay, so I tried to explain you what is sigmorphisms. I tried to explain why it's so useful. Now let's return to the question that we began from. It is expression which in Russian it is Вернемся к нашим баранам. But it is French expression which was found in 15th century France, Gargantua of Pantagruel. In France, people don't use it very often, but okay, I'm sorry. It is in Russian, it's written Вернемся к нашим баранам. So let's return again to formal functionals. We have formal functional, which is nonlinear homomorphism, and I want to prove. So I don't have so much time. I think I will give idea of the proof of this theorem. So I have formal functional. Formal functional, again, it is every functional here has exact meaning. It is function on X. It is functional of order 1. It is functional of order 2, and so on. But some of these functionals, it is not converged. So I just consider some of these functionals as a formal functional. To every function G, the functional Lm assign it is functional of order G. So we prove now that formal functions which are nonlinear homomorphisms are pullbacks induced by sigmorphisms. So if I will prove this theorem, I think after it will be much easier to explain, to speak with mathematicians about sigmorphisms. We just will say sigmorphism it is something such that its differential is usual pullback. And that's all. Okay. Let me recall you what's nonlinear homomorphism. And here I have to recall you very carefully. So we consider arbitrary formal functional. We consider arbitrary formal functional, which assign to function G series of the functional. Of course, when Ian asked me question, what's a value? It is not value, it is series of the functionals. But this, let's take differential of this functional. If we take differential of this functional, it is usual pullback, but it is usual pullback which is taken on GDEq. It is a formal map. So Ka of x and g, it is a formal map which possesses zero term, it is genuine function, which possesses first term, and so on. Now my claim is that now I will find you sigmorphism such that pullback generated by the sigmorphism coincide with this formal functional. Of course, we have no choice. Let's consider arbitrary formal functional and consider the value of this formal functional on linear functions. If you consider value of this formal functional on linear function, we'll come to the master action. So I will reconstruct my action. And it is, I really have temptation to consider for this functional as a model, to consider sigmorphism generated by this action. And maybe pullback of sigmorphism generated by this action will coincide with L. It is what I'm thinking about, dreaming about. And it is really the fact, it is what I will do. Theorem. Suppose we have arbitrary formal functional. If we have arbitrary formal functional, I showed you that for arbitrary formal functional, you can reconstruct, you can take value of this formal functional on linear function, and you will come to the action. So we have formal functional, and let Sx be action associated with this formal functional. Then our formal functional is equal to pullback induced by sigmorphism in the case if L is nonlinear homomorphism. So nonlinear homomorphism, it is the maps which are very nonlinear, but in spite of these facts, we can approximate them by linear homomorphism. It's very beautiful property, which not so difficult, but I consider it very beautiful. So let me try to give you I have about 15 minutes. I will try to give you idea. Of course, I cannot give you the proof of the theorem. Honestly, I would be very happy if nobody will find mistake in my proof. The proof of the theorem which I proved. Of course, I cannot say it's a theorem because I'm in mathematical physics. I'm not a physicist, I'm a mathematician to say that I proved theorem. But okay, I proved something in the class of formal functionals, which sounds at least very promising, because after this statement, it will be much easier to speak about nonlinear homomorphism. Okay. So how I prove this theorem? We will consider. So suppose we already have formal functional L. For this formal functional L, we have action which generates this formal function. So let us consider sigmorphism generated by this action, but let's truncate this action. We can truncate, we can amputate this action at S1, at S2, SR. So it is what I do on the next slide. For example, here, I consider sigmorphism defined by generating function S0 plus S1. Here I consider sigmorphism defined by generating function S0 plus S1 plus S2. Here I consider sigmorphism defined by generating function S0 plus S1 plus S2 plus S3, and so on. For every time when I have sigmorphism, I can consider pullback induced by this sigmorphism, and I can consider functionals phi1, phi2, phi3. And I come to the series of the functionals. So my aim is that all these functionals tend to my functional, because I repeat, I began from the formal functional, which are based only to properties that it is nonlinear homomorphism. By this functional, I constructed series of the functionals, and I would like to prove that series of these functionals tend to my functional. Tend in what topology? Of course, because I work in the very weak topology, I consider tending up to the order 1, 2, 3, and so on. Okay. I will formulate now a statement. Of course, it is statement which is very easy to prove by, it's very natural to prove by induction. So let me formulate the statement. Step by step, we will show that for every m, formal functionals Lx coincide with functional m up to order m. So first, I will prove that it is that functional f1, which I constructed in the beginning, coincide with my functional L up to order 2. Then I will prove that up to order coincide with F2, F3, and so on. I will go by inductive later. So if I will take as inductive hypothesis that it coincides with, that my functional coincide with functional Fm up to order m plus 1, then it will coincide with the functional m plus 1. Every time when I say functional, in fact, of course, it is to sigmorphism Fm correspond pullback generated by this sigmorphism. Okay, let's go to see how I will prove the first statement. Proof of basis of induction. First statement I prove using just, you have formal, because yes, I make my problem much easier, because from very beginning I restrict my considerations by these functionals. So my functional is L0 plus L1 plus. So S0 is a function of S0 fx. Put G equals 0, we come to S0. It's very easy to see, it is not difficult to see, honestly, that we have functional S0 plus L1. So our functional equals L0. L0, it is a function S0x plus L1. Now let me prove you that these two terms approximate my functional up to the order 2. To prove here, I will use the fact that it is nonlinear homomorphism. I will differentiate my functional. And doing this differential, taking this differential, I will come to this conclusion. Okay, I don't think that it will be possible during my talk to look all these calculations. They are a little bit difficult. I just give idea of how to calculate. Now, next step, inductive step. Here, I want to speak a little bit. Suppose we already proved that our functional coincide with the pullback generated by mth sigmorphism up to the order m plus 1, because so you remember, let's see the statement which I put here. Yes, inductive statement. We suppose that L coincides with mm up to order m plus 1. Because it coincides with Fm up to order m plus 1, we can add this order m plus 1 and we write this statement. Now it is here where I would like to explain the idea of the proof. Of course, you know how difficult to deal with objects, with nonlinear objects. And I had not even hoped that I can do something. But in spite of these functionals are nonlinear, the last term here, it is linear. So to prove this inductive hypothesis, I prove that Ln plus 1, in spite of the fact that all the objects here are nonlinear, the last term is linear. And maybe the main idea of the proof, the main point of the proof is that it is possible to prove that this last term, because L is nonlinear homomorphism, the last term is linear. Okay, the proof is very simple. We just differentiate this map, and we come to the condition. So I repeat again, I had to prove that this last term is linear over G. Doing differentiation and doing some calculations, which we come to condition that it obeys to the following property. And playing with this formula, okay, it's very, very beautiful, but very interesting play, which I don't think that it is now time to speak about these things. And I come to this formula. So I think that I just will finish my talk, because it is here. You can see the proof, and I will be really very happy if somebody will find mistake. I don't think that I did mistake, but who knows? I hope that it is not mistake. But if I didn't make mistake, I repeat, the main corollary of my talk is the following: that if my talk is true, if my statement is true, sigmorphism can be defined much easier. Sigmorphism consider arbitrary nonlinear map from the space of functions to space of functions, which differential is linear, then it is sigmorphism. So in some sense, if you consider sigmorphism in category of sigmorphism, I have not time to speak about these things, but many notions of the classical mathematics of the linear algebra have very beautiful generalization in the category of sigmorphism. Okay, I repeat again, I think it is now time to stop. I think I stop. Better if you will ask questions, maybe I will answer. Okay, I finished my talk.
All right, let us thank the speaker. And if anyone has questions, please.
Yes. Again, you are asking question. I don't listen to you. No?
Я так понимаю, вы в основе положили что-то аналог диаграмм Феймана в квантовой механике.
Нет, просто нет. Я в основу не положил аналог Феймана. В основу я положил скорее нет. Я все время думал об этих, но у меня не получалось эти вещи. Я в основу положил анализ, нет, просто очень многие вещи, связанные с толстыми морфизмами, становятся понятными с точки зрения связи между классической и квантовой механикой. Но это тот кусок деятельности, the conception of sigmorphism which are defined, we deal with different manifolds. So in homotopy Poisson algebras, in the case if the manifold is the same, you can consider sigmorphism as analog of quantum mechanics over classical mechanics. But it is very special case. И в этом смысле, да, конечно, у меня есть какие-то новые.
Any more questions? All right, if we have no questions, let us thank the speaker again. And that's all. Thanks, everyone.
Thank you.